So now we want to take a look at the specific theorem that tells us exactly when the mixed partial derivatives are going to be equivalent. In other words, what are the conditions in which we do not need to worry about which order we do our differentiation? And this can be typically pretty useful because there could be cases where doing the differentiation in a specific order is easier than doing it in a different, an alternative order. So this is known as Clairaut's theorem, sometimes also known as Schwarz's theorem. So named after naturally Clairaut and Schwarz. So we're going to suppose that f of x, y is defined on, this part's a little bit new from what we've done. So we're going to suppose it's defined on an open disk, D. A lot of the theorems in single variable calculus start with supposing that f of x is defined on an interval, a, b, right? Now that we're opening up in 2 dimensions, we already saw a case where our domain looks more like a disk, right? Like a circle. So an open disk means that there's no boundary points, basically. So it's just the equivalent of being an open interval. So if we were defining like x squared plus y squared is less than or equal to 9, I think was the domain we came up with in one of the day 4 videos. Less than or equal to implies that there's a boundary there, right? Because you can be equal to 9. So we would just take out that equal to part and it would just be x squared plus y squared is less than 9. Then we have an open disk. Okay. So disk is basically, it's just the word just implies like some kind of circle, but then it's like the middle is shaded in, right? So like you have all of the points within that circle. So we suppose that it's defined on an open disk D that contains the point AB. Okay. So this is like equivalent to saying, suppose that f of x is defined on the interval AB and there exists some c inside that interval, right? So just bringing it up into 2 dimensions. So if the functions f of x, y and f of yx are continuous at AB, then f of x, y, AB is equal to f of yx, AB. Okay. So in other words, the derivative at that point, the second order derivative at that point, it doesn't matter which order we differentiated. Whether we did x first or y first or whatever, the mixed partial derivatives at that point will be the same. So if we want to extend this out from just a point into a general function, if the function is continuous at all points on that open disk, then the mixed partial derivatives will be the same at all points on that disk, right? So if we're looking at 2 continuous functions, at least where the second derivatives are continuous, then we don't need to worry about the order in which we differentiate. So we need continuous second order partial derivatives in order to not need to worry about the order of integration. So with most continuous functions, that's going to give us this, but not all of them, right? Like think of like the absolute value function, where the absolute value function is continuous, but its derivative is not continuous. But a lot of the more well-behaved functions we looked at, like the last one, for example, right? Here are second order partial derivatives. We just have e and sine, no domain issues here. So these are both continuous all of the second order partial derivatives are continuous. Everything in this is continuous, so we didn't need to worry about the order of integration. Same thing with here, right? Very well behaved function, no domain issues. Same thing, negative 8y minus 6, definitely a continuous function. So we don't need to worry about the order of integration here. Okay. Now the caveat to this is that you have to verify that both mixed partial derivatives are continuous, which would imply that you need to calculate the mixed partial derivatives separately in order to verify that they're both continuous. So it's kind of like, by the time you do that, you're already going to know if they're the same thing or not. But if you have, knowledge of these functions, like if you're dealing with a polynomial, for example, you know that that's continuous and it's infinitely differentiable. So, we know that those, in that case, the second order partial derivatives aren't going to matter. So by this point, I guess I'm just trying to say that you should kind of have a feel for which functions would cause issues in terms of its derivatives being continuous. So namely like the absolute value function, like the cube root function, for example, or really any root functions. They're going to have problems with their derivatives being continuous, right? Maybe starting like rational functions, so just the normal things that cause the domain issues. I think rational functions are usually fine, but just some things to look out for there. So typically in examples that we'll look at, this will be satisfied. So we won't really need to worry about the order of differentiation if we're taking a mixed partial derivative, but it's just not something that we can take for granted, and we need to verify it if there is any doubt.